Right, so there's a component in your car that has to let your two rear wheels spin at completely different speeds when you turn a corner. Otherwise your tyres would scrub and skip. And it does it with no computer, no sensors, just gears. And the way it does it is honestly one of the most beautiful pieces of engineering I've ever seen. That's number one. But first, 9 other mechanisms you use every single day and have absolutely no idea are even there. Let's start gentle. When you pull your handbrake, you're yanking a steel cable that clamps the rear pads or shoes. But here's the bit nobody mentions. Brake pads wear down, so that cable should get slacker over time, and your handbrake should slowly stop working. It doesn't. Inside most drum brakes, there's a little threaded strut called the star wheel that ratchets itself one notch longer every time you brake in reverse, automatically taking up the slack the pads leave behind. It's mechanical, it's self-adjusting, and it's been quietly compensating for wear your whole ownership. Neat, but wait till you see what's inside your gear stick. Every time you slot a manual into gear without a horrible grinding crunch, you're being saved by something called synchromesh. Here's the problem it solves. The gear you're about to engage is spinning at a totally different speed to the shaft. Ram them together and you'd shred the teeth. So before the gears ever touch, a little brass cone friction locks against a matching cone, dragging both to exactly the same speed in a fraction of a second. Only then does the collar slide home. You feel that tiny resistance in the lever right before it engages. That's the synchro doing its job. Older gearboxes didn't have it. That's why Grandad double declutched. This one genuinely threw me. In a hydraulic power steering system, how does the car know which way you're turning and how much help to give? There's a device called a rotary valve built right into the steering column, split by a twisted metal torsion bar. When you turn the wheel, your input twists that bar just a couple of degrees, and that tiny twist opens ports that route high-pressure fluid to one side of a piston, shoving the wheels for you. Stop turning, the bar untwists, the ports close, the pressure equalizes. It's proportional, it's instant, and it's driven by a bar of steel twisting by millimeters. Wait till you see what your brakes multiply your foot into. Press your brake pedal with your foot and you generate maybe 300 newtons. Nowhere near enough to stop a 2-ton car. So 2 hidden multipliers step in. First, the brake booster, a big vacuum chamber behind the pedal that uses engine vacuum to add several times your effort. Then the master cylinder squeezes fluid down thin pipes, and because that fluid can't compress, it transmits pressure to caliper pistons with way more surface area than the master piston. Small force, big area, hydraulic multiplication. Between the booster and the hydraulics, your gentle press becomes over a ton of clamping force. And it's all done before you've even noticed. Nowhere not before you've gone camp compress. And because that fluid can't compress, it transmits pressure to caliper pistons with weight. Your turbo is basically 2 fans sharing one shaft. And the trick is what spins it: waste. Hot exhaust gas on its way out anyway, blasts through a turbine wheel and spins it up to a genuinely mad 200,000 RPM. That shaft drives a second fan, the compressor, which crams more air into your engine so it can burn more fuel and make more power. So you're recycling energy that would have just gone out the tailpipe as heat and noise. The clever bit, that shaft floats on a thin film of oil. No metal ball bearings would survive those speeds. Free power from rubbish. But your suspension hides something even sneakier. Here's a question. When you hit a pothole, where does that energy actually go? Your spring absorbs the hit, but a spring alone would bounce you like a pogo stick for ages. So inside your damper, what people wrongly call the shock absorber, there's a piston forcing oil through tiny valved holes. That resistance converts the motion into heat. Your suspension is literally turning bumps into warmth in the oil. On a rough road, a damper can hit 100 degrees Celsius, and the valves are clever, they let oil through more easily on compression than rebound, so the car settles smoothly instead of kicking back. Speaking of clever fluid, your gearbox. Your spring absorbs the motion into heat. An automatic gearbox has no clutch pedal, so how does it connect the engine to the wheels without stalling at a red light? The answer is a torque converter, and it's genuinely wild. It's a sealed donut full of oil with 2 fans facing each other. The engine spins one fan, which flings oil across the gap and spins the second fan connected to the gearbox. At idle, the oil just slips so you can sit still in gear. Press the throttle and the oil flings harder, gripping tighter. There's even a third wheel, the stator, that redirects the oil to actually multiply torque when you accelerate. No physical contact, just spinning oil doing the work. Your engine's valves have to open and close hundreds of times a second, perfectly timed to pistons flying up and down. And if the timing slips even slightly, valves and pistons collide and the engine destroys itself. What keeps them in sync? A camshaft, an egg-shaped lobe for each valve, driven off the crankshaft by a belt or chain at exactly half crank speed. As the lobe rotates, its bulge shoves the valve open, then a spring snaps it shut. Modern engines even rotate the cam relative to the crank on the fly, variable valve timing, so the engine breathes differently at 1000 RPM than at 6000. It's a mechanical orchestra running flawlessly millions of times a journey. When you pull away smoothly in a manual, you're feathering a friction plate into contact with the engine's spinning flywheel. But here's what surprised me. When your foot is off the pedal, the clutch is clamped shut with enormous force, hundreds of kilos, by a big diaphragm spring. Pressing the pedal doesn't clamp it, it releases it, prying that spring back so the plate can slip free. So the default state is engaged, you're actively working to disconnect. That friction plate, riding between flywheel and pressure plate, is what lets you slip gently from stationary to moving without a jolt. Every clean getaway is you controlling exactly how much those surfaces are allowed to rub. Now, number 1. Here it is. When you drive round a corner, your outer wheel travels further than your inner wheel, so they must spin at different speeds, but they're driven by the same engine. Lock them together and your tires scrub and skip. The solution is the differential, and it's pure mechanical poetry. Inside sits a set of spider gears that let the drive split unevenly between the two wheels. Going straight, both wheels turn together and the spider gears don't rotate. But in a corner, those little gears start spinning on their own axis, feeding more rotation to the outer wheel and less to the inner, automatically, continuously, with no sensors. It solves the